Hey, welcome to the Explainer. Today we're diving into a new kind of AI that pretty much challenges how we thought machines should write. And you know what? It might be a lot more like how you think than you realize.
So let me ask you something. When you're thinking, do your ideas just show up one word at a time, all neat and tidy? Probably not, right? It's usually more like this, chaotic first draft that you then clean up in your head. Well, if you're nodding along, you've basically just understood the core idea behind a whole new approach in AI called text diffusion. For a while now, the big models like GPT have worked in a very linear way. They predict text one little piece at a time, what we call a token, from left to right. But these new diffusion models, they just flip that script entirely. They generate a whole messy draft of a response all at once, and then they revise it step by step, a lot like we do.
So, here's our game plan. First, we're going to dig into this new way of AI thinking. Then we'll compare it to the way things are usually done. After that, we'll pop the hood and see how it all works, check out the incredible things it promises, and finally, we'll ask that big question. Is this where AI language is headed? Let's jump in.
Okay, so let's start with that first big idea. What exactly is this new way for an AI to think? And why is it shaking things up so much? Well, the whole concept of diffusion actually comes straight from physics. I want you to picture a drop of ink in a glass of water, just slowly spreading out and dispersing. That's the basic idea. In the world of AI, it just means we start with pure randomness, what we call noise, and then bit by bit we refine it until it turns into something that makes sense, like an image, or in this case, a clear piece of text. Now, let's really get into the core difference here, because this is the fundamental split between that old linear method and this new all-at-once approach. So this is the classic way it's done. The model generates the word the. Based on that, it predicts cat, then sat. And it just keeps going, one word after another. And here's the kicker. Once a word is written, it's locked in. There's no going back to change it. It's final.
Now, check out how totally different the diffusion process is. It starts with a bunch of placeholder masks, basically gibberish. Then, in each step, it revises the entire sentence at the same time. It might fill in a couple of words, maybe even change a word it put in earlier, until finally, a clear sentence emerges from the chaos.
This is honestly the perfect way to think about it. It is not about getting everything right the first time. It's all about drafting and revision. The model spits out a full, messy first draft, kind of looks at it, and then asks itself, okay, how can I make this whole thing better? And it just keeps repeating that process.
So that's the what. But how in the world does this actually work? Let's peel back the layers and take a look at the mechanics of turning that random noise into perfect grammar. To really get this, let's use a little metaphor. Imagine a huge, fast landscape. And on this landscape, every possible combination of words exists somewhere. All the good, coherent sentences, they're sitting on top of these hills of high probability. And way down in the deep valleys, that's where you find all the random noise and gibberish. The job of a diffusion model is to start in one of those noisy valleys and figure out how to climb its way up to a peak.
Now, researchers tried a few different ways to make that climb. Some tried these hybrid models, others tried working with the numerical meanings of words, but that led to all sorts of rounding errors and other technical headaches. The real breakthrough, the one that got us here, was when they figured out how to work directly with the text tokens themselves. That's the state-of-the-art approach today.
But there was a catch. See, with images, diffusion is a bit easier because you can smoothly change a pixel from one color to another. But text is different. It's made of discrete, individual words. You can't just slowly morph the word cats into dog. To solve this puzzle, these models use a mathematical tool called Markov chains. The easiest way to think about it is this. If your first draft is the cat sat, your next revision only depends on that specific draft, not on all the messy steps it took to get there. It's a clever way to model these jumps between distinct states, like different versions of an essay.
The LaDAW model is a great concrete example of this in action. First, it gets pre-trained by just learning to fill in blanks in huge amounts of text, kind of like the early BERT model. Then, it's fine-tuned specifically to complete a response based on what a user asks. And finally, when you actually ask it a question, it starts with a completely blanked-out response. And, step by step, it unmasks the words until the full answer is revealed.
All right, so we've covered the how. Now for the really fun part, the why. What are the incredible promises of this new architecture that have so many researchers this excited?
10 times. Let that sink in for a second. We're talking about a potential speed increase of 10 times. For things that need answers like right now, think coding assistants, this is an absolute game changer.
And this isn't just a theory either. A study from ByteDance showed that on a top-of-the-line GPU, a diffusion model was hitting speeds of 1,500 tokens per second. A comparable traditional model, it was topping out around 200. That is a massive, real-world speedup, and it's mostly because this whole revision process can be done in parallel. And for the companies running these models, that also means a huge drop in cost.
But it's not just about speed. Diffusion also promises much higher quality. You see, traditional models can suffer from this thing called exposure bias. If they make one tiny mistake early on in a sentence, that error can just snowball into complete nonsense because they can't go back and fix it. Diffusion, on the other hand, can do what we call holistic correction. Because it sees the entire draft at every single step, it can catch and fix its own mistakes as it goes along.
And here's another superpower: flexibility. Since diffusion models don't have to work from left to right, they are absolutely perfect for nonlinear jobs. Like rewriting just the second paragraph of an essay or filling in a missing chunk of code. For a traditional model, that's a really awkward task. For a diffusion model, that's literally what it's built to do.
So, with all these amazing promises of being faster, better, and more flexible, where do these models actually stand today? Is this tech still stuck in the lab, or is it ready for prime time?
Well, if we look at the current landscape, we're already seeing models like Mercury Coder that are going toe-to-toe with really powerful models like GPT-4o Mini, especially in tasks like coding. And here's the wild part, they're doing it almost 10 times faster. This shows that in these specialized areas, they are already incredibly competitive.
So here's the bottom line. While diffusion models aren't yet the undisputed champions across every single benchmark, and I do mean yet, they have moved way beyond just being a cool research experiment. For things that need to be fast, like coding, or flexible, like editing, they are a powerful and very real alternative that's available right now.
And all of this leads to a really fascinating final question. The biggest challenge for text has always been that it's made of these separate, discrete words. There isn't a smooth path, no gradient between the word cat and the word dog. But what if a model could learn a proxy for that gradient? What if it could learn to navigate that landscape of words just as smoothly as image models navigate the landscape of pixels? That right there is the next frontier, and figuring that out could change everything. Thanks for joining.